about to start. Going live in 3, 2, 1. Well, welcome everybody. Today we are very excited to have Sam Kessler presenting their paper Same State, Different Task, Continual Reinforcement Learning Without Interference. Sam is a machine learning PhD student at Oxford University working on Bayesian continual learning, among other things. Sam, we are very excited to hear your talk today. I can't believe we actually have back-to-back weeks on the continual RL, so I'm probably going to be an expert on this topic now, I hope. Without further ado, please go ahead, take it away.
Awesome, yeah. Thanks for the intro. Pretty cool back-to-back presentations on continual RL. So it's a pretty, I guess, unexplored field. Lots of really cool, interesting questions. I'm going to present my paper, Same State, Different Task, Continual RL Without Interference. And this is work that I presented at ContinualAI for earlier this year. In essence, we look at this problem of interference in continual RL. And I want to highlight that this is actually distinct from forgetting in some subtle ways that I'll go through in the presentation. And again, this is one of the quirks with working with RL, basically. And I'm going to present a super simple method to prevent this interference phenomenon that we call OWL. Present some sort of empirical results to sort of back that up. I will also say that I want this to be sort of as informal as possible, and if anybody's got any comments, just feel free to jump in and ask any questions. And also, James mentioned that quite a few people catch up with these videos. I know that I do as well. So just feel free to ping me an email. I'd be more than happy to try answer any questions or arrange a video call or something. So this was sort of joint work with these fantastic people. Continual RL. So I guess most of us are familiar with continual learning, where we see sort of one task after another sequentially, one by one, and we are sort of required to solve all previously seen tasks without, while losing access to the training data. In continual RL, this is pretty similar. So we have access to one environment. This could be one Atari game, and we'll have a budget of, let's say, 1 million environment interactions with that environment. And then when we move to a new task, we then have access to a new environment that the RL agent is able to sort of interact with, and sort of different actions are going to affect the states differently in that new environment, but it no longer has access to the previous environments. However, it's sort of continuously required, let's say, in a horizon of let's say 100 steps. It's continuously evaluated on all the environments it's seen so far. A very sort of similar setup to the traditional continual supervised learning setups that you guys should be familiar with. What I will say is that there's also no sort of set definition of what continual RL is. I think back in the 90s, there was this paper called Continual Robot Learning, which has a sort of rather different definition to this sort of very sort of experimentally heavy sort of setup that we use nowadays, that has been sort of adopted from like the EWC paper and the progressive compressed papers. This is definitely a sort of interesting thing to look at. Different sort of definitions of continual RL, and sort of standardizing everything is something that the sort of community hasn't done yet. Continual RL, so different environments could be, for instance, different Atari tasks. As you see, the state spaces in these Atari tasks are super different from one task to the other. Alternatively, our different tasks could be different sort of grid worlds. And here you see that the wall and the gap have sort of changed, for each different task. And the sort of state spaces here are actually a little bit more similar from one to the other. And so in general, I guess the definition that we use in our paper is that a new task is a sort of separate MDP with a sort of task identifier. And so we have this, I guess, sort of continual or sort of augmented MDP with this task identifier that's traditionally used to sort of tell an agent, when a new task has sort of arrived. So in like EWC, there'll be some regularization that happens, or if there's some sort of functional regularization forgetting strategy, then some sort of functional regularization will occur. So we have this traditional MDP with tau, which is this sort of task identifier which can or cannot be used. And for instance, task agnostic methods like clear don't use this tau, and I'll go into that. I'll go into a little bit more detail about what clear is a little bit later. So just bear with me with a few of the basics with regards to sequential decision making, and I'll sort of go into the sort of the meat of the paper a little bit further down the line. So let's just take a step back, and so the fundamentals of RL is that we have an agent that produces sort of actions conditioned on a state, and it learns from rewards that are taken from the environment. So the environment, given an action that the agent takes, this will change the state of the environment, the new state, and the reward that is produced is sort of fed back to the agent. And I want to make two key distinctions with regards to different sorts of environments that we can use within RL. So one is a fully observable environments where the states are fully observable. So the state will fully define the environment. So environments like the sort of OpenAI pendulum or mountain car environments, I think they'll have, let's say, like positions and speeds and accelerations of the cars. So that sort of fully defines the environment. Alternatively, we can have partially observable environments, which are the sort of more interesting RL problems that practitioners usually look at. And this is where the state or the observation that's returned by the environment doesn't fully define what's going on in the world. And this is typically, as a sort of human, how we sort of interact with the environment as well. So for instance, the mini grid examples here, these are partially observable. So there's like the agent only sees like a 9x9 grid or a 7x7 grid in this sort of grid world, and the rest is sort of masked out. There's a sort of fog of war that's around the agent. So a little bit like Age of Empires, if there are any old Age of Empires players. Again, some more important objects that I'll be referring to pretty regularly. So we have states, a set of states, and typically in RL, this is very, very large. We have a set of actions that the policy is required to take. We have a reward function. So for each state and for each action that the agent can take in the state, there is an associated reward. There's a transition function. So for a state at a current time step, taking an action at that current time step, the world or the environment is going to sort of shift states. And so the state of the new time step is defined by this transition function. We have a discount. So we can discount rewards that are very far into the future by setting gamma to a number smaller than 1. We have this policy, which is super important. So we want to learn a policy to interact and maximize rewards in our environments. So this is conditioned on the current state. The policy needs to give us what the optimal action is. And we have this notion of action value function, which is also very important. So this is essentially like a big table. So for every state and for every action possible in that state, this gives us a real number, which tells us what the expected long-term reward is. And so, so the objective is, as I alluded to earlier, is to find this policy. So we have this argmax. We want to find this policy that maximizes rewards over some horizon at H, given some starting state S0. And we have some discount factor to sort of discount future rewards. So essentially we want to find a policy that maximizes rewards. So there's a lot of math just to say that we want to find a policy that maximizes rewards in our environment. And so the key to that, so the approach that we take is to learn an action value function for each state action pair. And so there are other methods that we can use, for instance, learning a model, and then from the model learning a policy. But we're going to use this this action value function to guide a policy. And so so we use Q learning in particular to learn. So let me take a step back. Sorry. So if the set of states is really enormous, we can't really learn what the expected long-term reward is for each state and for each action that the agent can take. And usually what you do is you parameterize this action value function with theta, usually with a big neural network. And so we want to learn these parameters theta to learn the action value function. And we do that by minimizing this expected TD error. The sort of the DQN paper provided quite a lot of the sort of tricks needed to optimize this objective. So things like target networks, so theta bar. So sort of slowly updating our target network with our current parameters theta, and using replay buffers. So this expectation in our TD error objective is not, these aren't on policy updates, so these aren't actions taken from the policy pi, but can be from a big replay buffer. And so that's how we can maximize our TD error to obtain an action value function. And we can learn a policy that's guided by this action value function by parameterizing a policy in the case of continuous action spaces. And so we use soft-act critic, which is a pretty robust continuous control method. So so if we have continuous actions, we can learn this policy pi parameterized by phi. And if we have discrete actions, we can just follow the maximum Q value. So we can just take an argmax in a particular state and use that as a guide. Cool. So so I've covered some of the preliminaries. So this is just some of the basics, a little bit about continual RL and RL and some of the algorithms that I'll be introducing in our work. So now going forward, I want to get into the sort of meat of the sort of the paper, and that is this idea of interference and how it's sort of different to forgetting and how they sort of interplay. I want to talk about our model to prevent interference and as well forgetting, which we call OWL. So it's a very simple model, so it'll be super easy to understand. And then I'll present some empirical results, and then I'll wrap up. So so interference. So I want us to, let's just take a super simple example, mental model first, so that I can sort of introduce this idea. And I'll then actually present a supervised learning example to sort of really bring it down to earth. So basically, if we consider this 4 rooms environment, so this is the environment where there are basically 4 rooms. The agent, which is the red dot, is in the top right room, and the goal is in the bottom right. So the goal is in green, and so the agent gets a reward of +1 if it reaches the goal. And so we would expect the Q value, so the expected long-term rewards for being in this state, and if we take the action to go down, to be high. And so this is the what I sort of mean on the left. So the Q value of the state, where the agent is in the sort of top left, and the goal is in the bottom. Sorry, the top right, and the goal is in the bottom right. And taking an action to go down should give us a high expected reward, because the correct policy is to sort of go down, traverse the wall, and get to the goal. So this Q value should induce the optimal policy. And then alternatively, if we take a different action, which is to go left, this should give us a low Q value for the particular state that we're in. So for this particular starting state where we're in the top right. And now I want us to consider a different task. So now I've shifted the goal. So now for this second task, the goal is now shifted to the top left room. And so now, in the first task, the optimal policy induced by the Q functions, or the Q values, would induce a policy to sort of go down. However, now in the second example, if we take the action down, there's no goal there. And the Q values, if we learnt exclusively on the second task, are actually going to be super low. And then vice versa. So if we actually took the suboptimal, so in our first task, a suboptimal policy would make us go into the left room. And if we took that action left for this second task, actually this will give us a higher, this should give us a higher Q value if the Q values were sort of learned exclusively just from the second task. And so this is sort of the sort of crux of this interference, or what I define as interference in this paper, and has been mentioned before in the clear paper. So previous work usually says, catastrophic interference and catastrophic forgetting are the same thing, and these two terms are usually used synonymously. What I want to highlight is that for continual RL, these are actually quite different. And in the clear paper, which is continual RL with experience replay, where they basically used this powerful distributed method called Impala, and basically just kept all the data lying around in a big replay buffer, and just replayed that data to the agent. And the authors kept the replay buffer across separate tasks. So the paper is very elegant, very simple. It's task agnostic. It's just saying, let's just keep all the data in a big replay buffer, persist that across tasks, and this is enough to prevent forgetting. However, the authors in that paper, they did highlight this potential issue of interference, but they didn't really explore it like we are in this paper. And so in this case, if we were to just keep data from these, we learn one task, we have a Q function that induces an optimal policy for one of these tasks, and then we start learning a brand new task and start observing brand new data, what will happen is that experiences from both of these tasks are basically going to interfere with each other. So, state, action, next state, and reward sort of tuples are sort of going to interfere with each other because the agent has this sort of same starting state that are exactly the same for both tasks, but very different reward signals. And so this is the phenomenon that we want to highlight in this work. So, distinct from forgetting, there's this interference problem when we have sort of changing reward signals across tasks. And I just want to bring it back a step and show how this can arise actually in supervised learning. So there's this multi-MLIS data set. I think it was originally used in one of Jeff Hinton's papers. But basically it's just stitching together 2 or 3 or 4 separate, but in this case, just 2 separate MNIST digits and stitching them together in the same image. And for one task, so task 1, which is in red, so there's no bounding box. I'm just sort of, for the sake of illustration, putting a bounding box to sort of highlight what the task is. But for one task, the agent needs to classify the top left digit. And then for the second task, the agent needs to classify the bottom right. And so, we can see that the conditional distribution, so the probability of a particular label given the image is multimodal. So we can see that there's going to be some sort of conflict here between separate tasks, and we need a way to be able to sort of fix this conflict, basically. And so so let's learn these 2 tasks continually. So let's learn the first task, which is classifying the digit on the top left, and then the second task. And so now, at the end of training on the second task, we can then evaluate on the first and the second task, and we can use our favorite sort of continual learning strategies like EWC or gradient episodic memory in the bottom row. And this is great. We can solve these 2 tasks if we are using a multi-head setup where we have some sort of distinction about what task we're looking at. So now we can sort of model this multimodal distribution. And now let's do exactly the same, but now let's remove the multi-head setup. Let's make this completely task agnostic. Let's just use a single head. And we get massive catastrophic forgetting of the first task. So, and this is despite using a pretty powerful, like 2 very, pretty robust continual learning strategies. Obviously not the best, not state of the art, but they're pretty robust. I'd expect some form of remembering. We'd all expect some form of remembering here, but it's truly abysmal. Like, it's basically solely focusing on the first task, and completely forgetting the original task. Sorry, it's solely focusing on the last task that it's seen and forgetting the first task. I think I got that the wrong way around. So this is this interference phenomenon that we want to highlight, and this interference phenomenon will induce massive forgetting in this particular example. But at the same time, it could mean that our algorithms are completely intransigent. For instance, if we have let's say in the clear example, lots of data from our first task and very, very little data from our second task, it's just going to remember the first task. not learn the second task at all, for instance. So yeah, this is the crux of the issue in continual RL, where we have environments which have the same or very similar state spaces, but very different reward functions. So I don't know if there are any questions right now, but I'd be happy to take a little break and answer anything, just because this is the sort of key points I want to sort of highlight in this paper. Okay, I didn't get a signal from you, James, so I'll just continue. So yeah, so basically this idea of using different heads, seems to be very powerful, super simple, and is very well known to the community. And so yeah, this is basically what we tried in Continual RL. So the drawback now is that during training we need some sort of task supervision. So because we have a sort of separate head, we've got to be able to tell the algorithm what task it's in, so that it can learn on the specific head. So this specific head prevents interference and is distinct from how it's previously used within supervised continual learning. So previously, the head was sort of used as a sort of store of knowledge to sort of help sort of supervised learners remember. But here, this is really trying to model the sort of multimodality of these environments. So it's a very different sort of function that the head is serving here. We share a feature extractor. So if we just consider DQN, we just have a Q function that's doing the heavy lifting. So the Q function will have this sort of feature extractor that's shared among all tasks, and we choose pretty standard continual learning strategies like EWC or learning without forgetting to regularize this feature extractor continuously as we sort of learn one task after another. And then at test time, we sort of really wanted to, I think, we really want our continual learning algorithms to be task agnostic, to be able to have greater autonomy. And so at test time, what we did was have a bandit algorithm play a sort of an exploration-exploitation game to sort of select the right head to really exploit in the particular unknown environment that it's seeing. And so we are sort of agnostic to the task at test time. So yeah, super simple, but yeah, pretty effective at sort of preventing these sort of interference problems. So yeah, a simple example from continuous control is where we have conflicting pendulums. So for one task, we want we want the optimal angle of the pendulum arm to be at, I think, let's say plus 45 degrees, and then for another task to be minus 45 degrees. And so, yeah, we're sort of testing this hypothesis that environments with the same states but different reward functions will be challenging for experience replay type methods. And just want to highlight, so in these plots, the shaded region is the current environment that is currently being trained on, or that the continual RL agent has access to get new states and rewards. And in this case, we use soft act critic as a sort of base algorithm for continuous control. The gray dashed line is this sort of top level upper bound on the performance. And the solid gray line is what happens when we use experience replay. And we can see that the episodic rewards at test time are actually quite a lot lower than the dashed gray line, which is the single task performance. Actually, I'll move on to the next slide. And so actually what experience replay is learning is depicted in C, in figure C here. It's actually just putting the pendulum arm at 0 degrees. So, whereas the optimal angles should be more at 45 degrees, plus 45 degrees and minus 45 degrees. And what we find is that if we use our setup, which is OWL, where we give it some task supervision. So this is with the Oracle. So at test time, before the episode rolls out, we tell it what task it is. So this is a sort of upper bound on the performance of our method. And so this is the orange line. It's basically getting to the level of the single task soft act critic, this gray dashed line. And then with the bandit, so inferring the correct task at test time, we're getting very close. We're sort of approaching asymptotically this performance in orange. And then there's this lifelong policy gradient method, which is on policy and a lot less sample efficient in blue. So yeah, this is pretty cool. It sort of validates our hypothesis that different tasks that share the same state space but have very different reward functions. There's going to be this interference phenomenon that experience replay based methods are going to experience, basically. And so we need to basically infer what task we're in to be able to solve them. So this is nice evidence to support that. And now we go on to discrete control. So discrete action spaces now. And this is mini grid. So just for illustration purposes, I've only got 3 tasks here, but we scale to more in the paper and more diverse tasks as well. So this is a lot harder. First of all, it's image based. We have sparse rewards, and this is partially observable. And yeah, so basically the same story. So if we use because we use DQN as a base agent and DQN as off policy, so we have this experience replay buffer. We can persist the experience replay buffer across different tasks. And so we have this sort of experience replay, this clear type approach that, as we can see, sort of suffers from interference. So for instance, task 2 is rarely learned. And when it is learned at the very end of training 3 times on a particular environment, it completely kills learning in the first task. So this is, and then our method, they do a lot better, and the adaptive method, where we have to infer the particular task, the particular head, by using a bandit and supplying sort of TD errors as feedback to the bandit, is really effective in being able to identify the correct policy head to use. And so here we highlight some of the feedback that's given to the bandit. So this TD error that I introduced earlier in the preliminaries is fed back as sort of feedback to the bandit, and the bandit has its own sort of internal state. So its own sort of internal sort of probability distribution on which sort of policy heads to pick. And we can see, so for instance, in the last row, it's really sort of trying out all the different policies. It's first picking arm 2, even though we've trained arm 3 for the third task. It's picking arm 2 a lot. It's realizing after a while that that it isn't optimal to solve the task, and then it switches to the correct arm 3, to then solve the policy. To solve the environment. Apologies. So yeah, so the cool thing about using this bandit is that we have almost like a policy over policies. It's like we have a policy over the separate sort of Q function heads that we can sort of pick and we can reuse for completely unseen environments. And so here we're sort of, I think we've trained our agent in red continually on 5 separate environments, potentially some door key environments there as well. And here we can see that the bandit is sort of just like picking between these different environments and so it's picking between these different policies and using separate policies at different stages of this environment and eventually solving them, which is really cool and sort of alludes to hierarchical RL, where in hierarchical RL you have a policy over individual policies, and the policy over policies decides when to use a particular base policy. Obviously, RL is super brittle, and there are some pretty hilarious failure cases on the right. And so the bandit method is actually incredibly effective in generalizing to completely unseen environments, and a lot better than and a lot better strategy than experience replay or picking the arm using the best Q value. So you almost need a little bit of stochasticity, a little bit of exploration to be able to eventually settle on a good policy to then solve the environment. So, for instance, in these single crossings, we can solve close to nearly 40% of all the environments just after seeing 5 of them, which is pretty cool. Or the double crossings, we can solve like 20% of them just after continually learning with just 5 of these base environments, which is really cool and sort of points in the direction of sort of continuously building up separate skills and then having a sort of a policy over policies to sort of select a particular skill to then use at a correct time point. So this is a really cool, fascinating direction to sort of go in future. Just to sort of recap, I gave a little bit of an overview of sort of continual RL and RL and how that sort of fits together, and then I talked about this difference between. So in this paper, we make a distinction between interference and forgetting, and how interference can induce forgetting. I then talk about our super simple method, OWL. I think it stands for continual RL without conflict or something. Somehow we managed to boil it down to OWL. I gave some empirical evidence to sort of show this interference phenomenon within RL, and how just using different heads is a sort of really powerful strategy to combat it. The one downside is that we need to have task supervision during training, but at test time, we use a bandit to infer the particular policy head or the particular task that we're in, and this is remarkably effective and also points to a nice application of skill reuse. And so that is basically the journey of the paper. So I've just covered a little bit of a summary, and so sort of future work. So task inference to prevent this interference problem is particularly important. So we tried using uncertainties with like probabilistic Q functions. This was very difficult to use practically. We got some cool results using probabilistic Q functions, using ensembles, which we used in our continuous control experiments, but it just wasn't powerful enough at training time. So last week we had a cool presentation about a simple task agnostic baseline, and they used this idea of just an RNN, and somehow the history of the RNN is able to infer the particular task. I think that's a really interesting piece of work. I'm not too sure how I'm not too sure how it's inferring or why it's inferring the particular task it in, but it's a really cool result, and yeah, I'd be interesting to see what sort of leads on from that. And also some interesting work is, so what we had was a separate task head per task, but obviously there's like a linear scaling in the number of heads per task, and this doesn't allow for transfer learning to be particularly efficient. But if we had some sort of non-parametric distribution over the heads, this could allow sort of parameter reuse and sublinear growth in the number of heads. So yeah, so these are some potential future directions leading on from this work. And so, yeah, with that, I'd like to thank everybody. And yeah, as I mentioned earlier in the talk, for those of you watching on YouTube, sort of catching up, as I usually do, feel free to ping me an email. It's at the very beginning of the slides. Should have probably left my email here. But yeah, so yeah, thanks everybody.
Awesome. Thank you so much for the talk. I guess we have time for a few questions. I see we have only one joiner on Teams today. If you have a question, feel free to unmute and ask. Or if you're following on YouTube Live, just drop it in the chat and I will relay the question. I'll go ahead and start with something that may be completely off the mark because I usually work in standard vision tasks, some language tasks, but not RL. So please, Paul, correct me succinctly if you need to.
Yeah. No
But one thing I wonder is, why should RL tasks, or why should these RL agents be task agnostic? That's something I always wonder, and it's something that actually, as you talked more about, I'm kind of wondering if like there's this distinction between like in these scenarios, different levels versus different games. If that's almost like the distinction between class incremental, task incremental classification, where different levels is almost like expanding the task of this. This is almost like expanding the single task with more data, whereas like switching from playing Atari to a completely different game is a more natural. Use a different head, we can infer the task kind of thing. So I'm just wondering, like, am I correct in thinking maybe it's more important for like almost like this expanding with more levels versus like a completely different game, or should you be able to drop an agent in any game and automatically like infer what game you're playing, I guess?
Yeah. So so I think there are lots of really interesting questions there. Yeah. So in terms of so let me just recap. So one question was what is more important being so you had one question about is it important to be task agnostic,
Right.
and then this distinction between sort of different Atari games, which are definitely like very sort of distinct games, versus sort of different levels, maybe sort of different permutations of the same game.
Like, so I think the interference might be, my intuition would be interference might be kind of higher when you're expanding your knowledge of this Atari games with more levels.
Well, so to answer that second question, so the clear paper, so this continual learning with experience replay paper, most of their experiments were with Atari, and so in that paper, what they did was they had some base RL algorithm that was off policy, or that was sort of semi off policy. So it had lots of data in this big replay buffer, and they found that let's just persist the replay buffer across all our tasks. And they used Atari games, and they didn't have this interference problem. So in one of their experiments, they mentioned this sort of interference versus forgetting problem, and they basically just sort of, in a sort of hand wavy sense, they just said, okay, look at multitask performance versus single task performance, and actually if we stack up the single task performance, we get the same performance as if we do multitask. So this interference phenomenon is not a problem. And so in these Atari games, they showed that interference wasn't a problem. And my I think my intuition, or where I'm sort of going at with this paper, is that because the state spaces are so different in these Atari games, task inference just isn't a problem. Like, you don't need to, like, you can be task agnostic in Atari games. And the main challenge with Atari games is just having a big enough model, being plastic enough, and obviously having the compute to sort of train across multiple Atari tasks. So interference, I'm pretty sure is not a problem for Atari tasks because the games are so different. You don't need to have to infer the task. And then, yeah, your original, the other question was, yeah, what's more important, sort of separate environments, or sort of separate games, like Atari games versus sort of separate levels?
I'm sure they're both just. I don't want to say one's more important because I think they're
Yeah,
very different. I'm just maybe
yeah, they're
trying
sort
to
of,
go off what you just said, which is maybe one of them the interference is a big problem, and the other one is not so much. Um,
yeah. So, yeah, I guess they're just sort of different sort of settings.
right.
So traditionally in the RL community, like Atari is sort of seen as a sort of a benchmark where I think just in general within RL, the community is mainly focused on how well is like single task performance, and let's come up with algorithms that do well for a single task. Occasionally there'll be some papers that let's put all the separate Atari games together and let's have one agent that can sort of learn all of these together. Um, and then there's also this other separate literature, which is like meta RL, which is okay. Let's learn from a distribution of tasks, and then can we generalize to some unseen task? And yeah, typically things like mini grid or some sort of robotic environments. I've definitely seen some continual RL papers use them. We'll let's say just generate some random different gravities for like a walker to train on, and then so in meta RL, let's train on a distribution of gravities, and then we'll give it a brand new gravity configuration, and then a few shots just be able to learn. So yeah, that's the sort of setting from meta RL, and so yeah, again I guess I'm from my point of view was just sort of taking the sort of different tasks. So the mini grid examples, for instance, that's a traditional sort of meta RL type problem, or there's definitely been some cool curriculum learning work that's been done on it, or exploration as well. Like, it's a very hard exploration task. But yeah, just taking those sort of different tasks per se, and naively they look very simple. It's just a wall, right? And I feel like any sort of continual learning agent should be able to solve that before going on to something super difficult like Atari, basically. Yeah, so I wouldn't say one's yeah. So because the sort of state spaces are pretty similar with these sort of mini grid environments, it just means that you can have these effects like interference. That said, from meta RL, if you train on the entire distribution, right, of mini grid tasks, if you pre-train on some big distribution of mini grid tasks and then continually learn on let's say some brand new mini grid tasks, I would probably expect this interference problem to sort of go away because there's already a really good value function that has been learned from that. So yeah, I just think they're sort of just separate sort of
Right.
situations to sort of look at.
Thank you for your answer. Sorry to put you on the spot for some
No
abstract
problem.
discussion
And I
there.
feel like there were lots of really good questions there. So I think I only answered two of them. So feel free to to ask another question as well.
Okay. Are there any other questions? Um, I'll close with one thing. One thing when we were just discussing your answer just then, something that makes me think of where maybe this same state space type of interference problem might be really important. This could be completely wrong, but I'm thinking in terms of hierarchical RL, in the sense that if you have this big overarching goal such as StarCraft, and then you have like you need to be able to infer these subtasks and appropriately respond to them as it goes on and on. And I'm wondering if that's the first thing that comes to mind, besides just like some some robot working in a fixed space where distribution shifts over the time. But the other thing would be something like this kind of subtask hierarchical RL that could be completely bogus, but that's something that came to mind during your discussion just then.
Yeah, yeah, 100%. So, yeah, this is also something I've definitely been thinking about, how to sort of compose separate skills and sort of put them together. Um, there's actually a really cool new environment called Crafter, which is basically like a 2D, it's like a 2D, what's it called, Minecraft. And there, yeah, you're rewarded for like acquiring separate skills. So something like creating like an axe requires you to be able to like cut down wood, mine iron ore, etc. So that is almost like sort of how do you develop sort of separate skills and then sort of remember them and sort of compose them to be able to uh, sort of get even more reward, get even like sort of achieve an even better objective, which is like to get like an iron pickaxe, and then you can like do even more stuff, for instance. So yeah, that reminds me of that really cool environment, and I think in general that's super new. Um, And I think the benchmark in that paper is this model called Dreamer v2, which is like a super powerful model-based RL method, which is pretty exciting and it's a cool model. But to frame that as a hierarchical RL method is just, yeah, I think beyond where hierarchical RL is right now. I've tried to use hierarchical RL for some simple mini grid tasks, and it just doesn't work. um, so if anybody can email me a good hierarchical RL method that that can actually solve like a base single mini grid task, that'd be awesome. Because yeah, I think that's sort of where like I'd love to see continual RL going, like continuously building up skills and then composing those skills with like hierarchical, like in a hierarchical way, so have like a policy that sort of decides what skill to pick. And if it's in a brand new environment, let's instantiate a brand new, let's learn a brand new skill. Yeah, I think that is something that in my head seems really cool. um, I could be completely wrong,
No,
but
I agree. And
yeah.
we have someone in my lab, an outstanding lab mate who works on hierarchical RL, so I'll tell him to hurry up and
Oh
solve it
yeah,
so that
that.
we can
Well, no, no,
start
no. If you
adding
could,
the continual.
I'd be, I'd be more than glad to have a conversation there. It's just I tried one method, like a pretty well-known method, and yeah, just failed pretty badly. So yeah, that was a good month of my PhD gone. Yeah.
Awesome. Well, if there are no more questions, I guess we can go ahead and wrap up for today. Thank you, everybody, for joining, either live or at a later time. Thank you, Sam, for this wonderful presentation and answering all these abstract questions at the end. So today was our last seminar before the summer pause. So thank you, everybody, for helping with such a thrilling spring. We covered a wide range of hot continual topics, including ending with this continual RL papers. We'll see many of you at the CL Vision workshop in CVPR in just under 2 weeks. If not, I hope you have a safe, fun, and productive summer, and we will resume these seminars in the fall. So thank you, everybody, and goodbye.
Awesome. Thanks.